Good afternoon there, Year 901, Mr. Herman here, and by popular demand, I've made a video tutorial for your next exercise. Unfortunately, I cannot be there with you in class. I was told by a doctor's orders to stay home Monday and Tuesday because after my tooth extraction, I managed to end up growing or obtaining a blood clot within my mouth. I can talk now, but I'm in a lot of pain while talking, while eating, while keeping my teeth still, or chewing, or sleeping, or anything. So hopefully by Wednesday I should be good and I can get straight back into teaching. But for now I'm kind of on bed rest, but that's not going to stop me from making my video tutorials. So yesterday you would have worked on exercise 4b. You would have worked on worded questions for using the inverse trigonometric identities. 4c is looking at the applications using angles of what we call elevation and depression. The learning goals for this one is to know how angles of elevation and depression are measured in conjunction with the trigonometric functions. And the success criteria for this is to be able to draw and label an appropriate diagram from a word problem description and identify a right angle triangle, and to also know how to apply the correct trigonometric relationship or inverse trigonometric function to solve a problem. Now, elevation and depression, there's two new terminologies that we'll be introducing. Before we get to that, what I want you to do is to write this as your title with today's date. Now I'm recording this on the 2nd, so in your case today's date will be the 3rd of the 8th 2021. Wow, it's already August. Now before we get to this, we want to do a recap. We always do a little bit of a recap of what we do know. Okay, so what we know, what we've been looking into from exercise 4C, not 4C, sorry, 4A and 4B. What we do know is our trigonometric identities, and we do know that the sine of an angle, it's not sin, it's pronounced sine. The sine of an angle is the opposite over the hypotenuse. The cos of an angle is the adjacent over the hypotenuse. And tan of an angle is the opposite over the adjacent. If you are to give me a right angle triangle and within there you give me an angle and one of these lines, I can solve for the other line, and we just got to figure out which trigonometric identity we need to use given the lines in relation to the angle that has been given, or the position of the angle within a right angle triangle. So ka toa is a little chant or saying that we use in order to remember which identity that we should use in relation to the angle. You can always have this written down at the top of your page. I tend to, or I used to anyways, when I used to answer these type of questions in school, all the way to university. So katoa, really helpful. So what we do know are these trigonometric identities when solving for a line. The other thing we do know is the inverse trigonometric identities when trying to solve for an angle. And this is pretty much the same thing with this little power of -1. This is just to indicate this is an inverse. Whenever you see this, you know we are solving for an angle. So same relationship over over h rather, when using inverse of sine. Cos inverse is a over h, and tan inverse to find the angle is over a. So again, you can use the so katoa little acronym or little saying to help you out with inverse trigonometric identities. This is to look for an angle if two lines have been given. So looking into applications of elevation and depression is a combination of both identities and inverse identities within a worded problem. And either we've been given an angle of elevation or depression, or we need to try to solve for the angle of elevation or depression. But what is the angle of elevation and depression. So new subheading, angles of elevation and depression. So the angle of elevation. So the angle of elevation. And as you can imagine, when we use the term elevation, we think of the word up. So the angle of the elevation, this is measured, and its angle is measured up from the horizontal. And the horizontal is just a direction of a line that goes across from left to right. So horizontal, opposite of vertical. So the angle of elevation is measured up from the horizontal. So we start at the horizontal and we move up, and wherever the trajectory of the line goes, this angle here would be the line of elevation going up. And so the opposite of this is the angle of depression. And the angle of depression, as you can imagine, is measured down. It's measured down from the horizontal. There we go. The angle of elevation is measured down for the horizontal. So angle of elevation, angle of depression, the use of video software editing, I love it. The angle of depression, these are the two different types of angles, the terminology of angles anyways, that we'll be looking into, and they just are treated as opposites. One's up and one is down. And this the diagram that I'm going to show you now is the best way to visualize this. So this diagram here, just taken straight from the textbook, we can see that the horizontal line here, when measured up from it, will be the elevation. There is also another horizontal line here, and when you're going to measure down for that horizontal line, this is considered the depression. Now, because these horizontal lines are parallel, the elevation and depression angle in this particular example are the same because they are alternate angles. Okay, so that could be a clue to help you out when tackling certain questions given within the textbook. Now please remember, at any time if you are writing this down into your book and you need the teacher to pause the video, please indicate to the teacher to pause it, so that way it's not going too fast and you feel like you're rushing to get these notes down straight away. Okay. Now different students have different approaches in solving worded type questions, and you will see a lot of worded type questions when tackling angles of elevation and depression, and any type of questions that use trigonometric identities and the inverse. The best way, and this is taken straight from the textbook, and there is one more little thing I'm going to add to this. The best way to solve these type of problems, it's good to visualize and draw a right angled triangle and add any given information that has been provided to you within the question. You're going to use a trigonometric ratio to find what it is that you're looking for, whether that be a length or an angle, or sometimes you can look for more than one length. Maybe you can look for two lengths, but you will always be using one of the trigonometric identities or ratios, or the inverse, in order to solve for the unknown. And then with all worded questions, and you should be used to this by now, you should answer the question in words. If the question is given to you in a word format, your answer should be in a word format. So you will be using that therefore symbol. Alright, so remember your therefore symbol, which is the three dots that look like this. So whenever we do all working out and everything's all said and done, you're going to answer in word format, and you're going to use this therefore symbol. And therefore it just means from the information that we've obtained or worked out prior to this, we can conclude that, and then you can state your answer. Now I did say there was another thing that you can also do. A lot of you guys, if anything most of you guys, write your questions out into your book, which is a really good thing to do, because the more examples that you have in your book for your common assessment task or for your exam, the better position you are, because you're getting exposure to different examples and different ways to tackle a question. So when you do write your question into your exercise book, it's good to, and I'm going to put this up the top there as well, it's good to highlight. It's good to highlight or underline any important information. Now, important information, this is it is very subjective. A lot of students think that important information is just the numbers, but I like to think it's also to do with anything that's deemed important regarding direction. So yes, numbers show units, but as we're looking into elevation and depression, that can determine whether the angle is going up or down. There's also uses of direction in regards to north, south, east, west that you might see pop up as well. Okay, any type of information that is deemed important, highlight or underline this. Okay, this will stand out within the question, and so that way you're not feeling too intimidated or overwhelmed when it comes to tackling worded questions. I know this is a tactic that many students use, especially when you're moving into the senior years. Okay, so let's have a look at a few examples. I'll get them ready now. All right, first example, again taken from textbook. We have a helicopter that is hovering at an altitude of 250 meters. The angle of the elevation from the helipad to the helicopter is 35 degrees. We're going to find the horizontal distance of the helicopter from the helipad to the nearest centimeter. All right, let's have a look. What can we extract? What information can we extract, underline, highlight in order to tackle this question? So go ahead and write this example out. While you're writing this example out, what I do know is altitude of 250 meters. So here's this altitude word. That means from the ground up, it's 250 meters. So it's hovering in the air, 250 meters. So we've got a helicopter, 250 meters up high. The angle of elevation from the helipad to the helicopter is 35 degrees. 250 here, so 35 degrees. So angle of elevation from the helipad to the helicopter is 35 degrees. We're going to find the horizontal distance of the helicopter from the helipad to the nearest centimeter. So let's visualize this. We've got a helicopter, and you can go ahead and draw some really detailed helicopter. My one is just gonna look like that. Don't spend too much time trying to make it and there's a little window with a pilot. Hello. Alright, so there's a helicopter, and this is hovering at an altitude of 250 meters. So from there up is 250 meters. This is what we do know. The angle of elevation, okay, so the angle of elevation from a horizontal going up, and this is from the helipad. Obviously that helipad has to be on the ground somewhere. So I want to draw the ground, and the helipad is somewhere along here. Alright, so there's a helipad right there. And we do know is that it creates an angle of elevation from the helipad to the helicopter. So angle of elevation is up from the horizontal. So we're looking for an angle that goes up here. And so that means if we draw a line from there to there, this angle that goes up, which elevates, is 35 degrees. This has to be 35 degrees. And what we're looking for is the horizontal distance of the helicopter to the helipad. Now there are two forms that we can visualize it. Helicopter to Helipad, we're looking for this distance here. But that distance there is literally the same as this distance here. So this unknown, which I'm gonna deem x in meters, is what we're looking for, this horizontal distance here. Let's write our trigonometric identities. So Toa, we are looking for a length, so we're just using a normal trigonometric identity. We're not using an inverse because the angle has been provided. And what we can do is, I'm going to draw this triangle out again. Right angle triangle, 250 meters, x meters here, 35 degrees as our angle, and we're going to label this accordingly. What has been provided to us is the opposite line, so opposite from the angle, so O, and the line that we're looking for in relation to this angle is the adjacent. So what we're going to be using, which involves O and A, is tan. So let's write down this formula out, or identity rather, out. We can say that the tan of 35 degrees is equal to 250, because that's our opposite, over x, which is the line that we're trying to look for. Some students like to write the identity, just for safekeeping, is equal to O over A, but at this point right now you should be used to this. This should be stated without having to read it off a book. You should know that tan theta, at this point anyways, is equal to O over A. So we're going to fill in what we do know. Now remember, when the unknown is in the denominator, there was a little trick that I showed you without having to work this out algebraically. You can just swap the tan 35 degrees with the x. So what we end up getting is x is equal to 250 over tan 35 degrees. And this is just a matter of putting this into the calculator, and then in the calculator work this out for you. Trusty calculator, gonna get a fraction, 250 on the top. Remember to put your cursor down. We're using tan, 35 degrees. Make sure you close that bracket. And this is equal to 357.03. So 357. And because of that 7 that's there, this bumps up to 357.04. So 357.04 meters. And just make sure we're gonna find this to the nearest centimeter. So to the nearest centimeter is 0.04 or 0.04. Now this is a worded question. So therefore, and what is it that we're looking for again? We are looking for the horizontal distance of the helicopter from the helipad. So the horizontal distance of the helicopter, therefore, the horizontal distance, and we can just keep it as simple as that. The horizontal, that was checking, let's try that again. There we go. The horizontal distance is 357.04 meters. You can keep the solution as that. So we're going to go through one more, a bit more of a complicated example, and then I'll show you guys which questions that you need to attempt from the textbook. Alright, our last example for this before you guys get started on the questions. We are looking at two vertical buildings, 57 meters apart. 57 meters apart. Obviously vertical, they're tall buildings, not laying down on the ground. They're not lazy buildings. They're doing their job. They are 158 meters and 237 meters high. So we know that one is going to be higher than the other, as you can see in the diagram. We're going to find the angle of elevation from the top of the shorter building, which is here, to the top of the taller building, which is here, correct to 2 decimal places. So this one's very specific regarding the fact that it's an elevation. We know it's an elevation, so from a horizontal going up, but it's telling you from what point to the other point. So from the top of the shorter building to the top of the tallest building, we're finding the angle of elevation, and there's only one angle for this to be there. It's from there to there. Now the other things that we know is that the buildings are 57 meters apart. One of them is taller than the other. We've got 237, got 158, and we're finding the angle of elevation. Correct to 2 decimal places. So this here, I'm gonna recreate this right angle triangle on the side here, and we know that we are looking for an angle theta, so we have to use an inverse trigonometric identity. We also know that this is 57 meters. Now the hypotenuse within this right angle triangle has not been given, so we have to look for this length here, which can be found from this point to this point, but this has not been explicitly given to you. We can work it out because we know the height of one building and we know the height of the other building, so we have to take that initiative to find out what that is by finding the difference. Okay, and that will give us this length here. So it's obviously not 237, but it's 237 minus that 158. That will give us this height here, which is exactly the same as this small height here. So to find out in this case will be the opposite. So the opposite length. This is equal to length, the E. Obviously I'm creating this later tonight, that length A. This is the opposite length. This is equal to 237 meters. Take away 158 meters. I don't trust my maths right now, late at night, so I'm going to use the calculator. 237, take away 158. This is 79. So this missing link is 79 meters. Alright, we can go ahead and label this accordingly. What we do know, or what we do have, is the opposite and the adjacent. So, O and A, again, we're using tan, but we're not using tan, we are using inverse tan because we are trying to get an angle. So inverse tan of the opposite over adjacent, so 79 over 57 meters. So my theta, my angle, is equal to inverse tan. So remember to press the shift button and then the tan. You should see a tan to the power of -1. Get your fraction and put in 79 over 57. What is that? And we've got 54.19. 54.119. I know this is 19. It's asking correct to 2 decimal places. So 58.18. The next number is 8. So my critical digit is 8. This is higher than 5, bumping that 8. The second 8 up to 9. So 54.19 degrees. Therefore, the angle of elevation 54.19 degrees. And that's it. That is all there is when it comes to angles of elevation and depression. Nothing new. It's just an extension of exercise 4 and 4b with 2 new terminologies, elevation and depression. Let's have a look at what questions we need to do. So your log sheet, it's a bit cropped, let's just fix that, there we go. So your log sheet, you've worked on 4a and 4b. What you should have worked on yesterday was questions 5, 6, 7, 8. When I do come back into school, hopefully it is on the Wednesday, we can recap on some of those questions. I might give you some more worded examples so you can get some more exposure to the type of questions that you're going to see on your CAP. Applications using angles of elevation and depression. Questions 1, 2, 3, 4. Question 8. Question 10. You have 2 lessons to work on this. So you got this lesson and you got the next day's lesson, which will be Wednesday the 4th. The textbook questions itself, I've used the examples from the textbook. So if you want a more thorough explanation within there, you can go ahead and double check that. But if my set of examples makes sense, you don't need to. There are the questions for 4C. This is page 282. Best of luck, guys, with this exercise, and hopefully I'll see you guys on Wednesday. My mouth is on fire. I'm gonna get a heat pack. Have fun, guys. I'll see you guys soon, hopefully. Bye.